Welcome back. This module is going to cover time series decompositions. What is a time series decomposition? Well, in order to understand that, let's refresh our memory about something I told you the first week. So the first week I said there were 4 components of a time series. Time series decompositions will help us identify those components. So the components were seasonal. So seasonal effects happen at regular intervals. So if we have monthly data, maybe every December our sales spike, and in every January they drop. So that would be an example of a seasonal effect because they happen every December. Now, we talked about cyclical and trends. Remember, the trend part refers to a long-term pattern in the data. So maybe if you look at our sales over time, there's a linear trend or maybe an exponential trend. So that refers to a long-term pattern. Cyclical refers to a midterm pattern. So what I mean by midterm is for a while our sales are increasing, and then maybe for a while they're decreasing, they're below what you would expect in the trend line. We're not going to try to distinguish between cycles and trends. So we're just going to have a cycle trend part of our decomposition rather than trying to separate those two pieces out. I think the regression models that we did last week do a really nice job of capturing the long-term pattern, and what's left over is going to be the cycle plus the random part. In this module, we're combining the cycle and the trend part. So that's one way to think of this. So what a decomposition is going to do is help us understand what is the seasonal part, the cycle trend part, and then everything else. And so really, what you should remember about decompositions is that they're primarily used for description. Now we'll see that we could potentially use these also for prediction, but we're going to have much better models for prediction later on. So I would say basically use this for description only. Okay, now what's going to be very important is another concept from the first week, which is whether we have an additive model where we've got some seasonal trend that gets added to a cycle trend, and then the errors get added, or whether the seasonal effect is multiplicative, where every December my sales increase by 10% over what they were in November. That would be a multiplicative seasonal effect. Or the trend could also have a multiplicative effect where things are growing exponentially. All right, so that whenever we have those situations, we're going to use a multiplicative decomposition. Otherwise, we'll just use an additive decomposition. So here's what we're going to do in this lecture. I'm going to start out by talking about moving averages. Moving averages are going to be the way that we can identify the cycle trend component of this. Once we know about moving averages, I'm going to go into the classical multiplicative decomposition in some detail. There's also an additive decomposition that I don't intend to cover. So it's available in the same function in R, and it's covered in the textbook. But I think the multiplicative situations are much more common in marketing and business, and so therefore I'm only going to focus on that. But it's worth reading about the additive as well. I'll go over briefly some of the newer decompositions. So the classical decomposition has some problems. There have been additional methods proposed to address those problems, and I'm not going to go into them in detail, but I want you to be aware of them. And then we're going to talk about seasonal and trend strength measures. Okay, so I think a picture's worth a lot of words, and so this is where we're going to land. So there's a function in R called decompose. I can pass to decompose a TS object, and then maybe I say whether it's multiplicative or additive. And when I plot what comes back from this decompose function, I get the following picture. So what we see is the original data, then it decomposes the original data into, here's the seasonal effect, and we can clearly see that every fourth quarter our spike in sales. This is the cycle trend. So it looks like Amazon sales are increasing over time, and not only are they increasing, it's increasing at an increasing rate, probably exponential, which is what we found when we logged the data. And so the last part of this is what's left over. So what's left over after you've removed the seasonal and the trend part is what we get with this remainder function. Okay, so I believe these decomposition plots are very valuable. And when I first get a time series that I'm studying, this is going to be one of the first plots that I run just to understand what's happening. So that would inform choices that I make later on if I want to do some predictive or prescriptive modeling with it. But this is going to be one of my first diagnostics to look at. Okay, well, let's start with moving averages. So moving averages are really just a form of nearest neighbor smoothers. So if you go back to my machine learning class, there was a fairly short video that talked about nearest neighbor smoothers. I'd recommend watching that because it covers that with a little bit more detail than what I'm going to be doing right now. So for now, let's just say we're interested in description. I'm not that interested in prediction yet. We're going to go there next week. Okay, what is a moving average smoother? Well, a moving average smoother has a hyperparameter which describes the number of nearest neighbors that I'm going to be averaging. And so the way we're going to define that in this class is order m, where m is going to be 2 times some counting number plus 1. And so the whole idea here is very simple. We're just going to take k points on either side of the point I'm trying to estimate and compute a simple average of them. So I can go over to my document camera and illustrate this. The idea is very simple, and I've drawn many pictures like this for my machine learning class. So let's say that this is my data, and if I wanted to estimate this point, the zero nearest neighbor, or order 0 moving average, would be take 0 neighbors on either side of this point and average them. Well, this would be the estimate for the 0 nearest neighbor smoother. So if I connect my dots, I get the estimate for the 0 nearest neighbor smoother. Well, we're going to use black ink. I don't know if you can tell the difference between black and blue. All right, if I take one value, so k equal to one value on either side of a point and average them, I would take this point and this point. I think the average would be about here. Then if I want to estimate this point, I would average these points, and I think the average is about there. For this point, I would average these 3 values, and it would be about here. So maybe I get a function that looks like this. So this would be k equal to 1 neighbor on either side, or you could call this the m equal to 3 moving average. So why 3? Because every time I'm averaging the values of 3 points to get my estimate. All right, so this would be a moving average of order 3 because I've got the point itself and then 1 point on either side of that point that gets averaged. So that's the whole idea of a moving average smoother. What do we do if we have even m? So if I want to have a moving average of order 4, and this would be very common if I have, for example, quarterly data. Well, I can't take the focal observation and then 1.5 observations on either side. So instead what I'm going to do is we're going to take half of the observation 2 away on the left and 2 away on the right. So each of those get half weight. Then the points next to it, the points adjacent to it, get weight 1, as does the point itself. And so that's the way we handle moving averages with an even order. The textbook gives a more general way to describe this that you may find a little confusing, and therefore I just stated what is a moving average of order 4 in a very simple way that I think will make some sense. So let me just go sketch it. If this is my time series, and let's say I'm trying to estimate this point, what I would do is I would take this observation gets half weight, this observation gets half weight, these observations all get full weight. So I weight down the points on the end of this spread. So m is just a smoothing parameter that controls how flexible the function is. We called this the nearest neighbor smoother last year, and we'll be talking about centered moving averages later. Sorry, non-centered. This is a centered moving average because we take the same number of points from either side of the focal point. Well, let's look at an example. I've gone back to the T-bill data, and what you're going to see in this plot is I've estimated the moving average smoother with MA and different orders. So I just decided to use odd orders. So I've gone from 3 up to 13. And what you'll see is a couple things. So first off, as I increase the number of points that I'm averaging on either side, the function gets smoother. So this red line is with only 3, it's of order 3, so I'm averaging 1 point on either side of the focal point, and it's still pretty wiggly. The whatever that tan function is the moving average of order 5, here's 7, 9, 11, and 13, and so 13 gets fairly smooth. In the limit, if I were to go to m equal to very big, what I'd get is just the average method. I'm just averaging all points. So on one end with the moving average, we get the average method from 2 weeks ago. Whereas if I go all the way to the other end, you can think of that as almost naive. I'm just using the point itself as the. I'm not making forecasts here, but that when we make forecasts, it would be the naive. So this moving average is kind of a way to balance somewhere in between having the average method and having the naive method. So the naive giving all the weight to the current observation versus average, where we just average over everything. I want to do 2 more things in this introductory video on moving averages. The first is I'd like to just show a couple quick examples in the media that use this moving average. And so the first one I've chosen is the very famous graph that you can find in just about every newspaper in the world showing COVID cases. And what we see off to the right is they've imposed a line on this that's labeled the weekly trend. So what weekly signals to me is that they are computing a 7-day moving average and plotting that here. One really important thing to notice about this is it's a 7-day moving average. It's not an 8-day, it's not a 6-day. The reason for that is if you used, for example, a 6-day moving average, this line would have some strange bumps in it, whether or not, because of whether or not you have the the Wednesday day that usually spikes, or whether you get the Sunday in that period, that could affect this quite a bit. So you usually want to select the order of the moving average to be equal to the seasonal period. So here we have a seasonal period of 7 days, therefore it's a weekly trend. Another thing to note about this is we're using this for descriptive purposes. We're not really going to be using this line to make a forecast of the future. That's not the intent of this graph. The intent of this graph is just to summarize the cycle trend that we're seeing. I saw another graph just over the past couple days. This was one from Deutsche Bank, where again, it's a 7-day moving average of how much people eat out at restaurants. So the point again is we got a 7-day moving average. The reason it would make sense is because eating out is probably cyclical. There's probably definite weekly trends where maybe people eat at certain restaurants more on weekends versus weekdays, or vice versa. And so that's why they're showing a 7-day moving average instead of something else. All right. The last thing I want to do is talk about forecasting with a moving average. So I've hinted at this earlier on in the video, but and I don't intend to spend a lot of time on this, because we're going to spend a lot of time next week and the week after on this topic, because the methods that we have then are better. But I'd like to get you thinking about some of the notation and the approach that we're going to follow. So let's say that we have no trend and we have no seasonality. If we've got a trend or seasonality, we're going to have to use a more complicated method. So all we've got is something cyclical and random as well. So a notation that we're going to be using going forward is this script L at time t is going to denote the current level. So we're going to call it a level. And the whole idea of this level is that in L sub t, we've kind of baked in all we know about this time series as of now. All right, so think of this as, what do we know about this time series? Where do we think the time series should be at time t? And that's what this current level is. Because there is no trend, nor is there seasonality, there's not a lot we can do. And so our future forecasts, so if I want to forecast out h periods, given what I know as a period t, my best estimate is just going to be the level we're at right now. Now, if I had a trend, then I'd want to take advantage of that. So, for example, if this were the plot, maybe the plot looks something like this. Well, clearly I have a trend, and if I want to forecast where I want to go, I'm going to do something more like what I had with the drift model. I want to estimate that trend, and then if I want to go one period out, I would take the slope and add one slope to the current level. If I want to go 2 periods out, I would go 2 slopes beyond the current level. But we're not in that situation. We're in this situation where maybe the thing goes up for a while, and then it goes down for a while, and then maybe it goes up for a while, and so forth. And so, since there's nothing regular, there is no systematic trend or seasonality, where do I think this thing is going to go next? It's going to be very much like the naive method, where I'm going to take my current point, the level, and use that as my forecast. All right, so that's what this notation means. My forecast h periods into the future is just going to be where I'm at right now. Think of this as being like the naive method, but with the naive method, we use the observed y value at time t. Now we're going to do something a little bit more sophisticated than that. So the two methods that we're going to start out with are the order m moving average, and next chapter is the exponentially weighted moving average. Exponentially weighted moving average is, I think, a beautiful method that we're going to use a lot, but I'm just going to kind of warm us up with the moving average. So we're not going to do the centered moving averages that we were using for description. Instead, we're going to just take the m most recent values, so this is really simple, and average them. Now, that average is going to give me the level at time t. So maybe it makes sense for me to go sketch this out, and maybe I'll make it a little bit bigger so that we can see this a little bit more easily. So let's say that I have a time series that looks something like this. I'm going to make it so it's going up for a while, and then maybe it goes down for a while, kind of like a random walk. And let's have the order 3 moving average. So let's take, for example, time period 3. So this is 1, this is 2, this is time period 3. What would be my level, so script L at 3? So script L at 3 is going to be, well, y1 plus y2 plus y3 all over 3. So think of it as the average height of these 3 points. And so I'm going to just guess that the average height is about right here. That line right there, just a little bit below that, because we have to average in that point. So let's just draw a line here. This is L3. And so my forecast of what's the next point going to be is simply going to be this L3. So we could say y hat at 3 plus h, given that I'm at time period 3, is just L3. All right, well, what about the next point? So this would be the 4th point out. I meant this to be at period 4. All right, so L4 would be L2 plus L3 plus y2 plus y3 plus y4, still divided by 3. So I'm going to go get my black pen, and it would be the average of these points, and we would get rid of this guy. And so the new level would be up here. So this would be L4, and that would be my forecast into the future. Let's just say that this, I think I added too many points that don't quite fit, but let's say this is L10, or Y10. What would be my forecast value for the next point? Well, it would be the average of those 3 points, which would be about here. And so that's where I would think my time series is going. So that's how we establish this level. A couple things about it. I've already hinted at this earlier in the video. If I take a moving average of order 1 to do this forecasting, that gives me the naive method. So that just says use the most recent value to forecast the next value. If I were to take my order to be all the values so far, or if I use my entire training set, then that gives the average method. So we can think about this as the moving average giving us something in between the naive method and the average method. So you see we're getting to be a little bit more sophisticated than those simple methods, the baseline methods that I introduced in week 1. All right, how do you do this in R? Well, I don't think it's easy. The MA function that your textbook author has given us doesn't do it, and the reason he doesn't do that, I think, is because he's going to encourage you to use EWMA, which is what we're going to do next. It is possible to do it using a function from the base stats package, it's called a filter. And don't confuse this filter with the dplyr filter. So if you've loaded dplyr and you type filter, you're going to get that filter. If you say stats : filter, you get the base filter function. And this filter, does something that we often want to do in time series, which is this moving average. So if I applied filter to Amazon, I'm going to give the 4 values next to it equal weight. So that's what this is. I want to give the 4 most recent values equal weight. This convolution method means I want to do a moving average. Sides equals 1 means I'm only looking backwards. I'm not doing a 2-sided smoother the way I was back here. So this was a 2-sided smoother because the focal observation, YT, gets averaged with points on both sides. Here, I'm only averaging points from my focal observation backwards, so using only one side. I don't think it's terribly important that you understand the filter option, but if you're curious, that's how you do it. Okay, that's it. Next video is going to come back and show you how to do the entire decomposition. See you soon.